In our universe, time isn't just a clock ticking away, it's a dynamic framework where past, present, and future are interconnected. Every heartbeat, every memory, and every moment adds to an ongoing story that shapes our lives and the cosmos. Today, we dive into the science behind time, not only exploring space but the very essence of time itself. We'll uncover how time influences our reality, governs natural laws, and challenges our understanding, revealing it as a powerful, ever-evolving force. Time is more than just a series of moments marked by clocks. It is the fundamental framework that governs everything in the universe. Every event, from the birth of stars to your daily activities, is part of a continuous process shaped by time. Every sunrise, historical event, and personal milestone fits into the larger timeline of existence. Time is the thread that connects all things, whether we're talking about the past, the present, or the future. Modern science shows us that time is not just an abstract idea, it's a measurable and dynamic dimension, similar in importance to the three dimensions of space. In fact, time and space are connected in what we call space-time. Together, they form the structure of the universe, determining how objects move and how events unfold. Time does more than just organize events. It also plays a critical role in the laws of physics. From the decay of radioactive elements to the way our bodies synchronize with natural rhythms, time is involved in every process. It affects everything, from the very small scale of atoms to the vast movements of planets and galaxies. What might surprise you is that time isn't as constant as we might think. Einstein's theory of relativity tells us that time can change depending on factors like gravity and speed. For example, time moves slower the closer you are to a massive object like a planet, or the faster you travel. This means that time isn't the same everywhere in the universe. Over a century ago, Albert Einstein's theory of relativity completely changed how we view time. His work showed us that time and space are not separate entities, but rather, they form a single interconnected continuum called space-time. To understand space-time, imagine it as a flexible, stretchable fabric that extends throughout the universe. Just like a heavy object causes a soft sheet to sag, massive objects such as stars and planets warp or bend this fabric. This warping doesn't just affect space, it also changes how time flows around these objects. The more massive an object, the greater the distortion of space-time. Think of it this way. If you place a heavy ball at the center of a stretched-out sheet, the sheet bends, creating a dip. In a similar way, massive objects like stars and planets create dips in space-time. These distortions are what we experience as gravity. Gravity, then, is not just an invisible force pulling objects together, it's the result of space-time being curved by mass and energy. The more mass an object has, the more it bends the space-time around it. This curvature has significant effects on the flow of time. For example, in areas near extremely massive objects like black holes, the warping of space-time is so intense that time itself slows down. This phenomenon has been confirmed by numerous experiments and astronomical observations. Clocks near black holes tick more slowly compared to those farther away, and the stronger the gravitational field, the more noticeable the difference in time. This effect is not just theoretical. Scientists have actually observed it in practice. For example, satellites orbiting Earth experience a slightly different passage of time compared to clocks on the ground. These tiny differences are due to the weaker gravity in orbit, which causes time to pass slightly faster for the satellites. Time moves in one direction. It's an irreversible flow, progressing from the past, through the present, and into the future. Every new moment builds upon the last, creating an ongoing, unchangeable timeline that stretches forward without looking back. This concept of time's one-way movement is known as the arrow of time. At the core of this progression is a concept called entropy, a measure of disorder or randomness in a system. Entropy explains why things naturally move toward greater disorder. For example, imagine a frozen lake. When the weather warms up, the ice starts to melt. As it melts, the ice moves from an ordered, structured state to a disordered liquid form. This change isn't an accident or a flaw in nature, it's actually a fundamental property of the universe. Systems naturally tend toward higher entropy or greater disorder over time. You can see this everywhere. Take a photograph that fades over time. Or think about how a building slowly deteriorates as it's exposed to the elements. These are examples of entropy at work, systems moving from a state of order to a state of disorder as time passes. The reason this happens is simple. It takes energy to maintain order, and systems in nature tend to move toward a state where energy is more evenly spread out, which usually means more disorder. This tendency of systems to evolve toward higher entropy is known as the second law of thermodynamics, and it is one of the fundamental principles of physics. It tells us that the total amount of entropy in an isolated system can never decrease. In other words, disorder will always increase, and as a result, time's arrow points forward. But why does this matter for our understanding of time? Well, it's this constant increase in entropy that gives time its direction. If entropy were to decrease, the past and future could become indistinguishable, and time wouldn't flow in one direction. But because entropy always increases, time can only move forward. Beyond the equations and measurements, there's a deeper question. Is time an actual fundamental part of the universe, or is it just a construct created by how we perceive the world around us? For centuries, this question has puzzled philosophers, scientists, and thinkers alike. While we all experience time as a continuous flow, some theories suggest that time might not be what we think it is. One such theory is the idea of the block universe. This concept proposes that all moments in time, past, present, and future, exist simultaneously in a vast, unchanging block. In this view, time doesn't flow like a river from one moment to the next. Instead, everything that has happened is happening, and will happen already exists, and we are simply moving through it. This theory challenges our everyday experience of time. We feel as though time passes and each moment is a step forward into an unknown future. But according to the block universe theory, that experience might be an illusion, a result of how our minds process events and our limited perspective of time. From this viewpoint, the flow of time is just a mental construct, not a physical reality. While this might sound strange, it's not just a philosophical idea. Some aspects of modern physics, particularly in quantum mechanics and cosmology, suggest that time might be more complex than we realize. For example, certain interpretations of quantum mechanics like the many worlds theory imply that every moment in time could be part of an infinite number of parallel timelines where all possibilities exist simultaneously. Cosmology also adds another layer of complexity. When we look at the universe on a grand scale, we see that time doesn't behave consistently everywhere. The curvature of space-time around massive objects like black holes and the concept of time dilation suggests that time can change depending on where you are and how fast you're moving. This raises questions. If time can bend and stretch in this way, is it a true dimension, or is it just an emergent property of the universe? Time travel has long been a captivating concept, sparking the imagination of people across cultures and centuries, from ancient myths to the pages of modern science fiction. According to Albert Einstein's theory of relativity, time is not as fixed and unchanging as we once thought. Instead, time is flexible. It can stretch or compress depending on the influence of speed and gravity. One of the key effects predicted by relativity is time dilation, which occurs when an object moves at a speed close to the speed of light or is near a strong gravitational field. The classic example of time dilation involves two twins. One stays on Earth while the other travels on a spaceship at nearly the speed of light. This effect is not just a theory, it's been confirmed in many experiments, and it's also part of the technology we rely on every day. For example, GPS satellites orbit Earth at high speeds, and because of time dilation, their onboard clocks tick slightly faster than those on Earth. So, moving forward in time, or time dilation, is very much a part of the physical reality we observe. But what about traveling back in time? This is where things get more complicated. While the possibility of traveling into the past seems to conflict with what we know about causality, physicists have proposed a few theoretical models that might allow for time travel. One of these models involves wormholes, hypothetical tunnels through space-time that could connect distant points in time and space. Another theoretical construct is closed time-like curves, paths in space-time that loop back on themselves. In theory, these curves could allow for time travel, but they would require conditions that are beyond our current technological capabilities, such as exotic matter. So while moving forward in time is firmly supported by the principles of relativity, traveling backward in time presents significant challenges and paradoxes. Our understanding of time travel remains speculative at this point, relying on theoretical physics to explore the possibilities. Time shapes every aspect of our existence, from the cosmic dance of galaxies to the fleeting moments of human life. Through science, we've uncovered its dual nature, a dimension as tangible as space, yet as elusive as memory. Einstein's relativity revealed that time bends and stretches, entropy gave it direction, and quantum theories challenge whether it flows at all. Yet despite these discoveries, time remains one of the universe's greatest mysteries. What's clear is that time is both a tool and a teacher. It governs the lifespan of stars, the evolution of life, and the rhythm of civilizations. Our ability to measure it, from sundials to atomic clocks, has shaped human progress, yet its ultimate nature defies full comprehension. As science advances, perhaps we'll reconcile time's subjective experience with its objective mechanics, bridging the gap between mind and cosmos. For now, time remains a testament to the universe's complexity. It is a dimension we inhabit, a force we obey, and a frontier we strive to understand. Whether finite or infinite, absolute or illusory, time challenges us to keep questioning and to cherish the moments we have. Thanks for watching. If you enjoyed this video, don't forget to like, comment, and subscribe. There's so much more to explore together. Stay curious and we'll see you in the next adventure.